So in addition to all of the other stuff I have to read, I get a bunch of journals from the Math Association. This is the February issue of Focus, and in it is an article about using both physical 3D plotted items and another three-dimensional graphing software called CalcPlot 3D. And that is available online and does all the same stuff our grapher does. So I can graph the equations we want. There's our paraboloid. That's a little too big. Let's zoom out a little. But I can grab it and twist it and turn it just like we were doing the other day. I can snap it back to where it was. Oh, that reset to the original thing. That was what I wanted. Wait, let's put that back. So I have the ability to take this wherever I am. The grapher that's built into the MacBook, you have to have a Mac to access. You can access this platform independent. I believe there is even, this even works on phones. It's run on Java, so it's online availability is easy. But you can take these items, export them, and print them. And that's where I'm making all this crap that I was giving you the physical objects the other week for exactly that reason. Because you can draw right on those. PLA is easy to draw on with a Sharpie. So in a lot of cases where we start talking about contour plots and directions and derivatives and things, it might actually be easier to physically draw on a three-dimensionally printed object to see that. So I'm going to try and make more. But I hardly recommend the CalcPlot 3D software if you want to use something else. It works almost exactly like the MacBook grapher, but you don't have to have a Mac to use it. Okay. Question. We found derivatives in the X direction, derivatives in the Y direction. For some surface so I have this surface in 3D floating above the XYZ axis. And we found at some point, we found a derivative going in the X direction. And we found a derivative going in the Y direction. Right? So this is some slope. I don't know what it is. This is some slope. But wait a minute. When we did slopes, we did vectors. Yes? So there's a tangent line there. The line tangent to the curve at the point. It's the easiest picture. I'm going to stick with it. That one, right? So the line tangent to the surface in the X direction. I need the vector. What's the direction vector for this line? I want the line L1 that goes this way. I don't know what it is yet. There's another line, L2, that goes this way, right? That's the line tangent in the Y direction. I brought multiple skewers for a reason. Hey, wait a minute. Two lines at right angles to each other, right? The line one here goes parallel to the X direction. Line two goes parallel to the Y direction. Those are at 90 degrees. They make a plane. There's a plane that contains those two lines. And now, once again, I have a plane. It's going to contain these lines. There. Physically, you can see the two lines in the plane, right? So here's my question. What do I know about this plane? I know that in a small neighborhood, it touches that point and no other part of my surface, which means it behaves in 3 dimensions like this line behaves in 2 dimensions. I go back to Friday. What did we call that line? What kind of a line is it when it only touches the graph at that one spot and goes in the slope of the derivative? What kind of line is line 1? Wrote it down on Friday. Go back and look in your notes. So there's a tangent line, so it's tangent to this curve. There's a tangent line tangent to this curve. This plane that we were just looking at, this plane should be tangent as well. It should be tangent to my surface. On page 928, I have this picture, which is a much better picture than the one I've drawn. But you'll notice we've got curve 1, that's the curve we get by cutting in the X direction. And line 1 is tangent to that curve. And then we get C2, which is the curve we get going in the Y direction. And line 2, well, they've written T2, is tangent in that direction. And if I take those two lines, they make this yellow plane that is tangent to my surface. This plane that we've described is tangent to my surface. Tangent plane to the surface at the point. I would like to come up with an equation for this plane. Wait a minute. Wait a minute. Time out. What's the equation for any plane? Okay, that's a vector. N dot something equals 0, right? What's the something? I'm not sure that's the case here. What that was to find the volume of something, right? We did the dot product and the cross product together. That was a volume. Say that again. I need one other thing. Well, no, that works. I just need to know what this vector is, right? Now, P naught's going to be our point, right? And then this is just going to be an arbitrary point in the plane. So this was point X, Y, Z in the surface minus X0, Y0, Z0, our special point. Oh, wait a minute. That's a X minus X0 plus B, Y minus Y0 plus C, Z minus Z0. Right? That's the equation of a plane. Where ABC is my normal vector. But I don't know what those ABC values are. What I know are my partial derivatives. So let me think about this like slope. To get back to the picture, to get this curve, curve 1, I'm going to cut my surface along the x-axis. That's where this line comes from. But slicing that means I fix the y value. That fixes the y. I'm allowing x to move and I'm allowing z to move, but that fixes the y. So if I go to this equation and I get rid of that, I have the equation for a line. It's a line in x and z. That's this line right here. I know the slope of that line. Slope of that line is change in z over change in x, right? So let me take this equation and rearrange it. We divide by c. Z minus z0 equals minus a over c, x minus x0, minus b over c, y minus y0. With me so far? All I've done is rearrange. Here's the sneaky part. We fixed the y value. We're looking at a constant y, so only z and x are allowed to change. A over c is the slope of that line. Isn't that what we get from the partial derivative? That means this number right here should be a partial derivative. And it should be the partial derivative for this line. That's the partial derivative in x. So what's that number? Let's repeat the process. But this time we'll fix x and only allow y to change. That's this line. These numbers should be my partial derivatives. Holy crap, that means I can do this equation directly from the partial derivatives. Z minus Z0 equals the partial with respect to x at the point times x minus x0 plus partial with respect to y at the point times y minus y0. Okay, wait a second. Let me go back to the example we were doing with my hat. Let's do this one. Okay, so we were doing the function f of xy equals 3 minus x squared minus y squared. Wait, was that the one we did on Friday, or was it 4 minus x squared 2y squared? I don't remember. Which one did we do?
4 minus x squared minus 2y squared.
Then let's do that one. 4 minus x squared minus 2y squared. And we did it at the point 1, 1, 1. Well, that's x0, y0, z0 right there. And then we did the partial derivatives. Partial with respect to x and partial with respect to y were and then if I evaluate those at the point P, that's fx of 1, 1 and fy of 1, 1. And I get now, normally that's not the way we write a plane. We normally put all the variables on one side and a number on the other, but I can multiply all this garbage out. Minus 2x plus 2 minus 4y plus 4. Move those over. 2x plus 4y plus z equals 2 plus 4. Move the 1 over. I get a 7. Ready for the best part? There. There's the shape we're looking at, 4 minus x squared minus 2y squared, right? And we just came up with a new piece. Now, how do I add a new graph here? Is it that one? No, that's the zoom. Add to graph, new function. Now we'll create the new function. What new function am I going to create? I'll create the equation for the plane. Z equals 7 minus 2x minus 4y. That's what happens when you take our equation and get z all alone. Enter. Look, it touches the curve at exactly one spot. Just where we thought it would. At x is 1, y is 1, and z is 1. And there are all sorts of settings we can do to adjust this. Let's make it just a wireframe so we can see the paraboloid through it. We can see where they contact here. We can see the grid lines in the x and y direction. If you'd rather do this in Grapher, we can do the same thing, but we see exactly the tangent behavior that we wanted to. Question.
You said the contact point.
In a small area. right? Because remember, when we were doing our tangent lines, we would run into the same problem. Like, I would take a graph and I could pick a point here, and the tangent line near wouldn't touch anything, right? But if this curve had a turn and then came back down, well, then way out here it might touch. But in a small area, it only touches like the one point. Same thing is true with my surface. In a small area, it's only tangent really close. Let me put the other picture back up. I don't know what the rest of this blue surface looks like. It could look all sorts of wiggly and bouncy, right? And the more that surface looks odd, the more chance there is that we touch somewhere else. But in a small neighborhood, just that one spot. As a matter of fact, I can go so far as to say that as I zoom in, it will get harder and harder to tell the two apart, which is the surface and which is the tangent. Just like as we zoom in, it gets harder and harder to tell which is the curve and which is the tangent line. Remember? Long time ago, Calc 1. But I'm going to cheat. Here's the picture. Here's my surface. This is a different one. And there's my tangent plane. And if I zoom in, notice this graph goes from -4 to 4. This one goes from -2 to 2. Well, we're a lot closer together. This one goes from 0 to 2. We've zoomed in on 1, 1 a lot, and it's really hard to tell these two apart. Why? Because of continuity and because of having a derivative. We said this in Calc 1, that when you had a derivative at a spot, it meant that you could approach it with a tangent line, right? That made sense. The curve didn't get all whacked out as you came in. The surface is saying the same thing. As you get closer and closer and closer, it looks flat. It looks like this. At some funky angle, but it still looks like a surface. This is what bothers me with the flat earthers. We're too close. At a close enough scale, of course it looks flat. But we need the scale to be bigger to see the curve. More questions? I can play the same game that I played in Calc 1. Before I do that, though, shall we do another one? Let's pick another surface. I know. I'll go back and I'll find one of the funky pictures that we had from one of the previous sections. Remember those? On the homework, right? Bad. Let's pick one. How about this one? 5. We said that was cosine of square root of x squared plus square root of y squared. So, I'm going to pick what I hope is a relatively easy point. But it's going to give me some really sucky numbers no matter what I do, unless I rig this problem terribly. How badly do you want it rigged? We'll make our lives easy. Make the numbers easy. I'm not sure the answers are going to come out all that easy. I need the partial derivative with respect to x and y. Problem? Chain rule. Derivative cosine is. So negative sine of stuff. But wait, there's more. Derivative of stuff. The derivative of the square root of x squared plus y squared. I don't like doing the derivative like that. I'm going to write that as x squared plus y squared all to the 1/2, and I'll do it as power rule. So I get 1/2 stuff to the minus 1/2, but I just said stuff again, so that means there's another chain rule in here. What's the derivative of the inside stuff? That x2 will cancel with that 1/2. That means this x is going to stay on top. The sine is going to stay on top. And on the bottom, I'm going to get this square root x squared plus y squared. How is the derivative with respect to y different? Yeah. All the way at the end, I get a 2y instead of a 2x. So the only thing that changes is this x out here becomes a y minus y sine square root x squared plus y squared over square root x squared plus y squared. Bleh. Now we pick our point. I picked 1, 1. And when I look at that, I'm kind of annoyed because it means I need the sine of the square root of 2, which is gross. Negative 1 sine root 2 over root 2. Fy is the same thing. These are disgusting looking numbers, but they are both negative. You can get me a decimal if you want. I'm going to leave it just like that. But now I know the equation for my tangent line. Almost. I need one other piece of information. What other thing do I need to be able to get the equation for the line, the plane? The one thing I forgot. Well, not if I'm going to use this formula. Because then the normal vector is baked in there. But what in that formula am I missing? I got the partial derivative for x. I got the partial derivative for y. I plugged in the number. I got x0 and y0 because I have the numbers to plug in. What don't I have? Oops, I forgot z0. So I got to go back here and I got to plug in 1, 1 to the original equation to get the z value. But 1 squared plus 1 squared is 2, so I get the square root of 2, cosine of the square root of 2. I don't know what that number is. You're welcome to turn all of this into decimals. That's okay. Z minus cosine root 2 equals minus sine root 2 over root 2 x minus 1 minus sine root 2 over root 2 y minus 1. D minus number, slope, x minus number, slope, y minus number. I freely admit that sucks. But if we were to graph the two equations, it would, I think, make sense. Let me go back to my graphing device. Cosine normal. I got to zoom in. Hey, there, that's the right shape, isn't it? And at the point 1, 1, we should be about here, right? Isn't that where the hat is going down? My tangent line should be negative. My tangent line should be negative in that direction, negative in the y direction. Yeah, it makes sense for my plane to be at this angle. Whew. I forgot to share this on the Zoom screen, so let's share that on the Zoom screen so you see it on the video recording for later. There, now you see what it looks like. Okay. That shape looks ugly as hell. Trying to calculate values like this is going to suck, aren't they? Depending on my equation, it might be easier to work with a straight line than it is to work with the equation itself, right? So wouldn't it be easier to work with a plane than to work with some funky curvy equation itself? Chapter 3, section 10, linear approximations. The linear approximation for a function of x at some point A was the y value f of a plus the slope times the straight line x minus a. This was our tangent line. This was also the first two terms of our Taylor series. Well, guess what? Instead of using a linear approximation that's a straight line, I'll use the linear approximation that is the plane. So instead of actually trying to compute numbers on I wrote it down and then I forgot it. If I wanted to figure out the value at 0.95, 1.05, well, that's a pain in the neck, isn't it? But that's really close to the 0.11. Okay, wait a minute. What was the tangent plane we came up with? The equation for our plane. That was for the ugly surface. We're using this one instead. Go back to the previous example. Or z equals 7 minus 2x minus 4y, right? Wait a second. I can just put these numbers in here instead of in here. So z equals 7 minus 2 times 0.95 minus 4 times 1.05. What do I get? Did I do the arithmetic right? Now, let's actually go back and plug it in. What's 4 minus 0.95 squared minus 2 times 1.05 squared? Not that far off, huh? And plugging into the linear equation was a lot easier. I could do it in my head, right? Well, I can do this in general. If I have any differentiable function, my linear approximation in two variables is the equation for my tangent plane, which is just a whole lot easier to work with in general when I am working with complicated functions. But that's exactly what we were using to create our tangent plane, wasn't it? That's the same equation we used here when we rearranged and put it all on one side. Z equals derivative x minus a, derivative y minus b, and then I just move that to the other side. Right there. It's the same equation. I like working in planes. They're easier. Straight lines are much easier to deal with. But in order for me to do this, my derivatives have to be sufficiently nice. If I have problems with my first derivatives, this whole thing goes to hell in a handbasket. So if I run into a case where my first derivatives are not continuous, I'd have a problem here. So imagine trying to do this with a straight plane at the origin. Remember, we had different values going into 0, 0, right? My discontinuity is this all up, doesn't it? Okay. So the issue is that I don't only need my derivatives to be nice and exist, I need them to be continuous. If f of xy and partial derivative with respect to x and y all exist and are continuous at some point, AB, then my function is differentiable. So here, my definition of having a derivative requires me to look near a point, not just at a point. I need to look at the first derivative and the second derivative. Those have to be continuous also. Now, because I'm talking about continuity in the derivative, we will often see this referred to as a C1 function. Continuous in the first derivative. We'll also at some point talk about C2 functions or C3 functions or C infinity functions. So the idea of continuous how far down is going to matter in the long run. For the moment, I'm just looking at the first derivatives. Questions? Why? Back in the chapter in Calc 1 where we did linear approximations, we also said we could think of the differential dy as how much we changed when we moved a little bit in x, right? That's what that slope was telling me. Change in x, change in y. Well, now I'm changing x and y and measuring change in z. But I can do the same thing. And I can say, oh, the differential dz can be thought of as how much do we change z when we change x times the amount we change x. But also, how much do we change z when we change y times how much we change y. So I can measure this linear approximation by how far in x did we go, how far in y did we go, now how far up and down are you going? Ooh. Oh. Okay. An example. What's the formula? Not for a cylinder, for a cone. You have the internet. You do not have to have this memorized. What is the volume for a cone?
Squared times pi squared.
Okay. So 1/3 pi r squared h. Which also makes it, by the way, 1/3 of the cylinder with the same base. But I don't know if you've been out the Pennsylvania Turnpike going towards Hershey. Before you even get to Altoona, there's a gravel plant that makes crushed stone. If you're going up Business 66, going up towards Delmont, there's actually a facility on the side of the road that sells different types of stone, crushed stone for gardening and all, and roads and all that sort of stuff. There's another one in Pittsburgh, in Oakland. They have these giant conveyor belts that dump stone into a pile. I have a question. One of these conveyor belts is running. How fast is the height changing? How fast is the radius changing? I can measure that, right? I can stand there and I can measure. I say, oh, the radius keeps growing by this many inches, centimeters per hour. The height's growing by this many an hour. How fast is the production line going? How much stone is being made? Well, the change in the volume. Let's follow this process. What is the partial derivative with respect to r? of this expression.
Three, five, okay.
And the partial with respect to H so I can give you the change in volume 2/3 pi r h dr plus 1/3 pi r squared dh. And notice my units here. The units inside the parentheses are going to be length squared, radius and height, right? And dr is length per time. So this unit is cubic per time. Cubic meters per hour. Meters, meters, meters per hour, cubic meters per hour. That's a change in volume, isn't it? You take a sphere, and you paint it. You measure the radius before you paint it. You measure the radius after you paint it. You can tell me how thick the paint is, right? What's more, you can tell me the volume of paint you used. There was only one variable, right? Radius. If my tank is shaped like a cone and I paint it outside, and I can do the same thing, can't I? By measuring the change in the volume of the cone. You want error measurements. You measure the radius, you measure the height of a cone, but your instrument only goes to millimeters. So you could be off by 0.5 millimeter in either direction. What's your computed error, your propagated error on the volume? This is the way you compute that. It's sneaky. Propagation of error is really calculation in calculus, even though we do it in lab without even thinking about that, right? Questions? I like this idea. There's something sneaky going on here, comparing how much I changed X and how much I changed Y when I changed them both. But so far, we've only done a derivative in the X direction and a derivative in the Y direction. I'd like to do more. I'd like to do other directions. I need to get the chain rule better before I start doing that. So the next thing on my list of things to look at is a more detailed version of the chain rule. Once I've done that, I'll start looking at more detailed versions of derivatives. By the way, I did everything today in 2 variables. You want 3? Add another one on. Everything stays the same. I don't quite know what a tangent thing looks like there because I can't draw it right. But I can certainly do a differential in 3 or 4 or however many variables I need. But I'm not going to draw tangent things in multiple dimensions because I don't hallucinate like that. Questions? Wednesday's the chain rule. I think. Wednesday the chain rule is Wednesday question and answer. 3 cheers for having said. Wednesday is the chain rule, Thursday is question and answer. All right, we'll see you all on Wednesday. Have a wonderful rest of your day.